We'll wait for a few minutes for others to join. All right, welcome everyone to the week 6 tutorial of the course Fluid Mechanics. So I hope everyone is regular to the lecture videos and the assignments. In the last tutorial, we discussed about different kind of pressures and the classification of pressure measuring instruments. And we have covered all of the instruments so far. Those who have missed the tutorial, you can watch the previous week 5 video. Okay, and if you have any doubts, you can ask in the comment section of the video or of my YouTube video or anywhere else. So today we will be starting with hydrostats and hydrostatic forces. I hope I'm audible to everyone clearly. So just hold on, let me share my screen and let us start the session. Okay, I guess my screen is visible now. Okay, great. Also visible. So today's topic is hydrostats or hydrostatic forces. Hydrostats or you can say hydrostatic forces, right? So this concept was basically used for design of the hydraulic structures like dams, hydraulic gates, ships, submarines, or overhead tanks, etc. Okay, so let me write here. This concept is used for design of hydraulic structures like dams, hydraulic gates, ships, submarines, etc. Okay. So Don't worry about the notes PDF of this. I'll share it on the Google Drive, and you'll get the link from the Nptel team of the Excel sheet, and those who are directly watching from the uh, YouTube. So it's in the video description. You can see the Google Drive link. Each and every week, lecture, tutorial videos, PDFs are there. So my YouTube channel name is Nptel with Varnit. Those who have not seen ever, you can see directly from there. All right. So suppose there is a structure like this. Sorry. There is a gate structure like this. Okay. Suppose this is a gate, and there is a fluid like this. Okay. Or a reservoir like this. Okay. Which is holded by a gate. So actually there is acting an atmospheric pressure over the gate as well as a hydrostatic pressure on this gate, okay, which is varying linearly with the depth. Okay. So how is the atmospheric pressure acting? So atmospheric pressure is acting like this. So it is P atmosphere. So suppose this is your reference symbol for this reference level. So this is your atmospheric pressure, P atmosphere, which is acting on both sides of the gates. All right. P atmosphere as well as here P atmosphere. And this is your wall or gate, whatever you can say, wall. And if the water is there, reservoir is there, so there will be hydrostatic pressure as well, which will be linearly increasing, So let us draw that as well. So from here, you can say pressure is acting this. So what I can do, I can divide like this. The hydrostatic pressure and the atmospheric pressure. So this is the maximum. If the height of this wall is, that this reservoir is h, suppose from here to here, suppose this height is h. So this will be how much? This will be rho g capital H till here, and the remaining is atmosphere. So this is an absolute pressure condition. Okay, absolute steady. This is an absolute steady where you have gauge plus atmospheric, absolute steady. But we generally deal with the gauge studies. So this wall is somewhat like this. Let me again make. So suppose this is h itself, height, and this is p of the wall. But if I want to do the gauge study, I have to remove the, what we say, the atmospheric pressure from here. So I'll just drag this towards the center. All right. Now, if I want to h dash, let's say both are different. So let's say it's rho h dash, rho h dash. So if I want to do the gauge study, I need to remove the atmosphere pressure from here. So again, if I have the ball, the reservoir is this. Reservoir is still here. So only gauge pressure will be here this time. So if gauge pressure is here, no studies of the atmospheric pressure. So I have to remove the atmospheric pressure from here. So this is rho g dash till here. All right. And h or h dash, whatever you want. It's your wish. If you want the reservoir level to be exactly to the height of the gate, it depends all on you. And this is a gate study. Let me write here, gate study. But if you observe that the pressure, hydrostatic pressure, which is acting, it is linearly varying. So we need to find out the pressure, the net pressure of this hydrostatic pressure force you need to find out over this gate. And there is a center of gravity. There are 2 points. One is the center of gravity and one is the center of pressure. So center of gravity is nothing but the geometric center of the body. Okay. So if my body is like this, so my geometric center will be somewhere in the middle. So this is center of gravity. Whereas the center of pressure is the point where the net horizontal force is acting, the net hydrostatic horizontal force is acting over the wall. And it will be below the center of gravity. Because if you observe here, just by physical essence also, the more area of the hydrostatic pressure is towards the downwards. Okay, so it won't be towards the middle of this gate. It will be just below the gate. And we need to find out the value of the where it is acting and what the value of the pressure force is acting. So suppose this is your net FP pressure force is acting at the point that is CP, center of pressure, center of pressure. Okay. So there, we don't know what is the distance of center of gravity as well as what is the distance of center of pressure. So that also we need to identify. So how we will identify? So center of gravity is generally the geometric center. Let us say still it is x bar. X bar is your center of gravity position from the free surface, Whereas center of pressure is nothing but, let me use another color, at a distance of h bar from the free surface. H bar from the free surface. Okay. So if I draw the plate, isometric view of the plate here or the ball here, what do we observe? All the forces in a very well manner. So we take, or let us say this is P, width of the wall, and the height is h, complete height is h. Okay, so we can assume our elemental area here. Elemental area. Okay, we assume an elemental area which is at a distance of x, which is at a distance of x till here, and the width of this is dx. The width of this elemental area is dx, and the area is dA. Then the area will be dA. Okay, dA is the area of this. Okay. So there is a pressure, hydrostatic pressure, which is acting. So suppose the pressure here is at this point is P, and the pressure at this point is P plus dP, elemental change in the pressure, P plus dP. Okay. Just carefully listen this complete story, then you will understand that what is happening and how we are getting the values. So this is a pressure. So obviously because of the pressure change, that there will be a pressure force which will be there. So suppose this is your center of gravity line. This is your CG line. CG, which is just equivalent at this level. So if I guess made a bit lower, I'll again make it. So this and this line are equivalent. CG. This is CG, right? And the CG is at a distance from the free surface, that is x bar. X bar is the distance. So CG is the center of gravity. CG, center of gravity, and CP is center of pressure. Okay, center of pressure. So now there will be a total hydrostatic force, that is Fv, which you need to find out. So total hydrostatic force total hydrostatic force, pressure force or total pressure force, right? Pressure force will be, it is the net hydrostatic pressure force exerted by the fluid on the body. It is the net hydrostatic pressure force exerted by fluid on the body. And the value of this pressure force is Fp is nothing but specific weight into WA x bar. WA x bar. I'll derive this also how it comes. WA x bar. That is rho g into area into x bar. So this expression is valid for flat surface in any orientation. So flat surface can be at an inclination as well. Okay. So I'll write here this expression is valid for flat surface, not a curved surface. For a curved surface, we will deal in any orientation. Okay. So we know that what is the hydrostatic law? That is the gradient of pressure with respect to the distance, vertical depth, is equal to rho g. We have seen this in our previous tutorial. That is dp by dx is equal to rho into g. This can be applicable for both kind of fluids. If the fluid is compressible or incompressible. If the fluid is compressible or incompressible. Or incompressible. So we know that for an incompressible fluid, the density doesn't vary, but for a compressible fluid, the density will vary. Okay, so for incompressible, pressure will be just rho gx, whereas for an incompressible, if density varies, then the pressure will vary and the pressure force will also vary. For this, density varies. Okay, for this density varies. So let us do the derivation of the above expression of the pressure force. So how it comes. So we know that pressure is force per unit area. So elemental force which is acting here, on this element, let me make the force DFP, which is acting here. All right. So this is the elemental force. DFP on this element is nothing but pressure into elemental area, that is dA. Okay. So if you integrate, first of all, let us write again, DFP is nothing but, how will you write the elemental area? Width, that is pressure will be how much? Rho g hydrostatic pressure into dA. Rho g into x, that is the vertical, into dA. And now you integrate. So it's an incompressible. We are assuming that density doesn't vary. That is why density is outside the integration. If density varies, then this density will be inside the integration. So what do I mean from this? If density varies, then DFP integration will be G will be outside, rho X dA will be there. Okay, so density will be inside the integration. So rho is outside the integration. And what is X dA? So rho G is nothing but W, specific weight, into G, and X dA is nothing but X bar A. X dA is nothing but your first moment of area, So we can write it directly like rho G, no, rho G is W into A into X bar. So X dA, let me write, since X dA is nothing but X bar into area, which is your first moment of area. First moment of area. And you might have studied this basic thing in your mathematics also. So basically, what does it mean? For every elemental strip, moment of area is there from the free surface. So you have made a strip for this, a small this strip. So for every elemental strip, there is a moment of area which is equivalent to moment of area about the center of gravity of that point. And it can be written like this: X bar, that is the center of gravity, distance from the free surface into area of that body, and where X bar is your vertical depth of the center of gravity of body from the free surface. So I'll write here X bar is, so from here if you integrate it, FP comes out to be WA X bar as proved, WA X bar, and it is only for incompressible fluid, to be noted here because density doesn't vary. Incompressible for incompressible fluid, and X bar is nothing but vertical depth of center of gravity of body from free surface. From free surface. So this is your free surface. I'll write here as well. Okay, from free surface. All right. Now this was your, now what is center of pressure diagram or centroid of pressure force? This is a concept. That is center of pressure. So what is center of pressure? It is a point of application of total so you got the hydrostatic force Fp, and where it is acting, basically it is a point of application of total hydrostatic pressure force is known as the center of pressure, and it is measured in the vertical depth from the free surface. Everything is always from the free surface only. So it is point of application of total hydrostatic pressure force is known as center of pressure, that is Cp. Okay, and it is measured in vertical depth from free surface. From free surface. Okay. So for vertical flat surface, if you have a vertical flat surface, what is H bar? That is center of pressure point. So H bar is the symbol for this. I'll write here the distance H bar, center of pressure position. H bar is nothing but, for vertical flat surface, let me write, for vertical flat surface, even for inclined also we will see. First we will see for a vertical flat surface, h bar is nothing but IgG, that is moment of inertia, upon A x bar plus x bar. Ax bar upon x bar. IgG is nothing but moment of inertia of a body about centroidal axis. Centroidal, that is from where the center of gravity passes. This is your centroidal axis. This axis from the centroidal axis, okay, parallel to the free surface. So IgG is moment of inertia of body moment of inertia, basically MOI of body about centroidal axis parallel to free surface. And point to note here is that h bar is always greater than x bar. The height of the h bar is greater than x bar. It's much below, as I told earlier. That h bar will be a bit lower because from the physical sense also you observe that center of pressure is acting downwards, having a higher value towards the bottom compared to the above. Okay. Now, if there is an inclined surface, as I said, it is for a vertical flat surface, but for a inclined flat surface, for inclined, what will be the expression? If you have an inclined flat surface, let me draw a flat surface. Suppose you have like this, and it is at a depth, not even at just with the surface, free surface. It's some vertically below and inclined. The plate is vertically below as well as inclined. So how am I saying? Like this. So it's somewhat like the wall is something like this. Okay. So dashed line is the lead axis. So the gate is between the wall. So what is the pressure force which is acting on this gate? That we need to find out. So it is an angle of theta, suppose. This is your free surface. Okay. So again, you have some center of gravity point here. So this is CG, and the pressure force will be acting now. It is not directly like this. It's not a triangular because here also some pressure is there, which is acting. So it will start from somewhat like a pressure, then increasing, and then like this, somewhat kind of trapezoidal kind of scenario. Trapezium or trapezoidal kind of scenario. Okay. So this is your pressure which is acting. So pressure, again, there will be a pressure force at center of pressure, CP, FP, which is acting at CP. Okay. So center of gravity is the, what is x bar? It is the vertical distance from the free surface. So x bar is, again, as I wrote here, vertical depth, not an inclined depth. X bar is vertical depth. So x bar is how much? Vertical depth from the free surface, x bar, and h bar is again the vertical depth from the free surface to the center of point of action. So this is your h bar. Okay, H bar. That's a point of application where center of pressure force is active. So if this angle is theta, so this angle will also be theta from alternate angle theorem. Okay. Now I'm again drawing the isometric view of the plate to observe the forces. So this is, suppose height is h of this plate and length is like this. Okay. And the center of gravity will again pass through like this. CG, and CP will be just below that. CP. Okay, CP will be below that. Okay, and this is nothing but your gate right here. Okay, the gate to clear the gate exam. All right. Okay, so this is your point A. Suppose this is your point A. This is your point of the gate A and B. So what will be again pressure force FP here? FP will always be WA X bar. WA X bar only. And H bar is will now be what is the point where it is acting. So for this, the expression is IgG sine square theta upon AX bar plus X bar. And if you observe that if theta is 90, then the vertical gate will be vertical and it will be same as the above expression. IgG sine square 90 is 1 by X bar plus X bar. If theta is 0, then H bar will be equal to sine square theta will be 0. Then H bar is just this term becomes 0. So H bar is equal to X bar. So that is basically your plate the gate has become from inclined to horizontal. Okay, great. So how you get the value of X bar? So just by geometry you can draw here. If I show you, this is nothing but your triangle this time. If you observe this, this is your triangle. So this triangle I'm going, I think this is not visible. This is your triangle now. Okay, I'll draw this triangle here. So this distance was X bar. Okay, this was angle theta. All right, so this will be how much? Suppose I said this much is X1, this length. X1, if this is X1, so this will be X1 plus H by 2 till the center of gravity ends. X1 plus H by 2. Okay, so this tip is nothing but this point. This will be X1 plus H by 2. What do I mean? X1 plus this is H, so H by 2. So this is your hypotenuse of the triangle, X1 plus H by 2. So you know what is X1, you know what is H by 2. You can get the X bar, you know what is that angle theta from the given question. Now for different geometries, I'm going to tell you the values of the H bar. Okay, so suppose only a flat surface is there, vertical flat surface is there. Let me write here one by one for each case. So this is a free surface. I'll make the free surface altogether for all the cases. Okay. So my gate is like this. Yeah. The gate is like this. Center of gravity. This is CG. And this is CP. This is CP. Right. So X bar is vertical distance again. And CP is this much at a distance of H bar. The pressure force which is acting is this FP. Okay. And suppose this is at a distance of X1. Okay. This is at distance of X1. And the height of this is complete H. Okay. And if width is B, so I should have not drawn it like this. Let me change the figure like this. Directly showing you the isometric view. Okay, so if the width is B, so IGG will be written as, so H bar will be written as, so theta here is how much? 90 degree. If you observe, theta is 90 degree. H bar will be IGG sine square 90 by AX bar plus X bar. Okay, so it will comes out to be IGG value. What will be the IGG value here? It is BH cube by 12. So let us take this and this to be small b and small h. So BH cube by 12. Always remember one thing, that whatever, when the center of gravity x is cut, and whatever is the from the height, whichever length it is cutting, the cube will be of that much. Okay. So if the center of gravity is cutting h length, so cube will be of h. If the center of gravity cut b length, then it will be b cube. But here center of gravity is cutting the h length, so bh cube by 12. Now suppose instead of this rectangular plate, we have a triangular plate. Okay, suppose we have a triangular plate. So let me use a triangular plate. This is my triangular plate. So center of gravity and center of pressure. So center of gravity for this is, this is your center of gravity, and this is your center of pressure for this. Okay, so from this x bar will be how much? X bar is this much, x bar vertical depth from the center of gravity, whereas h bar will be how much? H bar is the vertical depth from center of pressure point. Okay, and the center of gravity is, if the height, complete height is h, capital H of this, so my point of the apex of the triangle will be at 2h by 3 from the center of gravity, from the center. And I, so this is a point of FP where the pressure force is acting. And my IGG value will be for this is BH cube by BH. So width again, B is the width of this. Let me write. Let us take small h only. BH cube by 36. Okay, BH cube by 36. All right. This is B. So this was for a triangle. Suppose instead of a triangle, I have a semicircle plate. Semicircle. So let us draw that as well. Suppose my plate looks like something like this semicircle plate of radius r. Okay. Okay. I think it looks fine. Again, center of gravity point will be, suppose here, CG, and CP will be below CP. Again, the distance of CG is x bar is nothing but x1 plus x1 is how much? This distance is your x1. So x bar is x1 plus r minus 4r by 3 pi. How? Because center of gravity from the base is at 4r by 3 pi distance. This distance I'm talking about. Let me make here. This distance from center of gravity to the base is 4r by 3 pi. This complete radius r this is r from this. Okay, center of gravity is so r minus this 4r by 3 pi plus your x1 is your x bar. So complete r minus this plus this much x1. Okay, from the geometry, and say it's a semicircular plate. So my again expression of IgG will be, it is 0.11 r to the power of 4, the radius of the semicircular plate. Okay, semicircular plate. I'll write here circular plate, semicircular plate. And suppose instead of a semicircular plate, I have a trapezium plate. Okay, so I have a plate like this. Okay, whose upper length is small a and lower length is small b. Okay, the height is capital H. Then again, center of gravity point. Center of gravity is at a distance of x bar. Okay, and this distance suppose is x1. Sorry. This oops. Yeah. So this distance is x bar and this distance is x1. This is x1. Okay, and suppose this is y. Center of pressure, again I'll draw center of pressure here. Also center of pressure was FP. Again here I'll draw the center of pressure. FP force is acting. Suppose this distance is y. Base to the center of gravity. Okay, is y. So this will be how much? The vertical left depth will be from the center of gravity. It will be capital H height minus small h minus y. Okay. So again here y bar value. Suppose this is y bar. This is y bar. So y bar value will be how much? First, the y bar is from the basis 2 into a plus b upon a plus b into h by 3 into h by 3. Okay, into h by 3. And IgG value will be a square plus 4ab plus b square by a plus b into h cube by 36. Sorry. Into h cube by 36. Okay. So these were all the expressions. Oh, I think I have taken it a bit towards the left. Just take it towards. Yeah, I think that works fine. All right. So this is our whole expression for all the different cases. We have a flat rectangular plate, triangular plate, semicircular plate, or the trapezium cube. Okay. Now I need to find the pressure values as well. So suppose we go to the cases like this. So my first case is, this is my fluid, free surface, and my plate is horizontal. My plate is kept horizontal. So again, we know that for a horizontal level, the hydrostatic pressure on a horizontal level is same everywhere. So it will be just pressure is rho gx. I'm always talking in terms of gauge now. Okay. Always it will be in terms of gauge. And center of gravity and center of pressure will be same here because theta is how much? Theta is 0. When I just told that when theta is 0, then h bar and x bar will be at the same position. So center of gravity and center of pressure will be same here. So Cg, or you can say Cp. Both are same. So pressure force which is acting is this much, Fp. And the pressure, if I draw like this, this is the pressure which is acting here. So pressure value is rho g. Suppose the x bar is, x bar and h bar are equal. X bar and h bar are equal here. So I'll use this. X bar is equal to h bar. Okay, so Fp will be how much? Pressure into area. What is pressure? Rho g x bar into area, that is WA x bar only. Okay, this is your Fp. And what will be the value of h bar? H bar is IgG sine square 0 by AX bar plus X bar. So it will be equal to X bar only. Okay, H bar is equal to X bar. All right. Second case, case number 2. Let us do. So horizontal vertical flat surface. So again, this is your plate like this kept here. Okay. So center of gravity will be somewhere here. And center of pressure will be somewhere here. This distance is how much? X bar. And this distance is how much? H bar. Okay, of the center of pressure. Suppose the plate is of width b and height h. Okay. So X bar is how much? The center of gravity, geometric center is at middle of the plate, H by 2, capital H by 2. Whereas the H bar will be IgG. That is B axis is cutting the vertical length H. Okay, so this axis is cutting this length. So cube will be of this length. BH cube IgG is BH cube by 12. Theta is 90. Sine square 90 is 1. Area is of this plate is B into H. X bar is at H by 2 plus X bar is again at H by 2. So from here it will come out to be 2H by 2H by 3. So position is 2H by 3. Again, the third case. If I have a circular plate touching the free surface, I have a circular plate like this. Okay, it's just touching the free surface. So again, the center of gravity is at a distance of X bar. This is your free surface. Okay, and center of pressure will be somewhere here. H bar. So X bar will be D by 2 if the diameter is D of this. If your diameter of this plate is D, and H bar will be, you can now find out by the expression 5D by 8 for this, 5D by 8. Okay. And the fourth case is a triangular plate touching the free surface. Triangular plate with the apex here. Okay. Base can also touch it, can be inverted plate as well. Two cases can be here. Okay. One case is like this, and another case can be like this as well. Suppose like this. Okay, both the case will have different H bar. So height again is for both the cases is H. Okay. So for this case, the center of pressure, the center of gravity suppose is at 2H by 3 from the apex we have seen before. Okay. The X bar is at 2H by 3. And center of pressure will be a bit below. That is, suppose H bar, and the pressure is acting like this. FT. So here, the H bar will be 3H by 4. Whereas for the other case, the center of gravity is here. CG, but center of pressure is always below CG. Okay. CP will be somewhere here. Okay. So if this distance was from the apex was 2H by 3, so from the base, center of gravity is at 2H minus 2H by 3, that is H by 3. Okay. From complete H, you subtract H by 3. And this is a center of pressure distance, that is from the free surface is H bar. Okay. And pressure force is acting here this time, FB. So this time H will be, H bar will be H by, if you put in the expression, you will get the values. Okay. So I think I've covered all the cases so far for calculating the value of the pressure force, how we calculate the pressure forces, what is that, at what point it is acting the pressure forces for different kind of orientation of the plates, and the values of H bar, IgGs. Okay. Now we will start with pressure diagram. So I'll just take a 2 to 3 minutes of break, and then we'll join. Meanwhile, you recap what has been done. All right. So let us start with pressure diagram now. Okay, topic of pressure diagram. So in what different ways we can calculate the pressure force? Okay. So one is pressure diagram. So hydrostatic force on a flat surface can be defined by analytical method or with a pressure diagram. Hydrostatic force, that is your FP. on flat surface can be defined by analytical method or your pressure diagram. Okay. So how we form the pressure diagram? So again, I have a free surface like this. Okay. So your free surface. And your plate is like this, or wall is like this. Okay. And isometric view of the wall will somewhat like this. Okay. So suppose the height is h. Sorry, I am writing d. And the width is b. Okay. Center of gravity again is at this position CG at distance of x bar. All right. And FP is acting here at CP. Okay. At CP. And h bar, just now we have calculated the value of h bar is 2h by 3. H bar is 2h by 3. Okay. 2h by 3. So if I see this plate again, so this was your point of CG. Okay. Center of gravity. If I make this plate once again, like this in here, in bigger sense, zoom view, like this. Okay. The width is B, and the height is H. Okay. I should have drawn it here only this side. So what is the pressure diagram looking like? It is increasing pressure. Hydrostatic pressure. Similarly, this way also. On this side also, because it's a three-dimensional plate. So can I do like this? So everywhere it will be acting. Okay. This is your center of gravity position. Suppose CG, and it is at X bar. CP, again, you know that. This is your CP, and pressure force is acting. Okay. And this value is how much? Rho GH. Rho G, capital H. The maximum pressure at the bottom. That's the plate. So what will be the volume of this pressure diagram? Volume will be area of this triangle into this width. Okay. This is a triangle. The pressure diagram looks like a triangle. So volume of pressure diagram is nothing but half into what is base? Rho GH. What is height? Capital H. This is area, and what is width? Capital P. This is the volume of your pressure. Okay. So how can I write? Rho G into H into B into H by 2. Can I write like this? Rho G is nothing but your specific weight, W. H into B is your area, and H by 2 is X bar. Center of gravity is X bar. Okay. So this is your pressure diagram volume, and this is nothing but equal to your pressure force HP. Okay. So volume of pressure diagram, PD is nothing but your pressure force. Volume of pressure diagram is nothing but your pressure force, WAX. One point to note here is that this pressure diagram technique cannot be used for circles, triangle, or other flat surfaces, other kind of shape of flat surface. This can be only used if my plate is a rectangular jar. Okay. Why? So again, the volume will change. Suppose if you have a circular plate like this. Again, if you want to make, this will be a pressure, then at this radial position, pressure will be there. This radial position, pressure will be there. Again, here, a pressure, single pressure. It's not a continuous volume. Okay. To get the value of the volume from here. All right, even if you have a triangular plate as well. So that's why. Another thing is, it is only applicable for rectangular flat surfaces, this pressure diagram technique. So I'll write here as a note. Pressure diagram method can't be used for circular, triangular, or any other shape flat surfaces. So far, we are dealing with flat surfaces only. No curved surface has come so far. It is only applicable for rectangular flat surfaces. Okay, this is one. One another way of analytical method can be that you just calculate the pressure at the center of gravity and then use area of the body and multiply with that. Okay, you find the pressure at the center of gravity. That is, if you have a center of gravity here, this is your center of gravity. You find pressure here, okay, instead of here at center of pressure. All right. So what I'll do, Fg, find the pressure at center of gravity, pressure force at center of gravity, and then multiply with the area. Okay. One analytical method can be calculate pressure at Cg, pressure force at Cg, that is Fg, and multiply with body's area. Okay, so what will be Fg? it will be rho g into x bar because center of gravity is at x bar. So it will be rho g x bar. Okay. And what is area? Area is, so using this, your FP will be Fg into area. That is rho g x bar into A. And rho g is W into Ax bar. W into X bar. This gives you the same result. Okay, use this technique for calculations. You can use this. Okay. Now we have done only a single fluid was there. That is any fluid, either it's water, oil. But suppose my plate is kept in a way, such a way that there are two different fluids. Then what will you do? Okay. So this expression, that is WAx bar of pressure force, is valid only for a single fluid. For two or more immiscible fluids, the pressure hydrostatic pressure force can be obtained by the pressure diagram. That's why we have this technique of pressure diagram, but only for a rectangular flat surface. I'll tell again. Okay. So case 2. Case if I have a plate with more than one fluid. Okay. This is my plate. Shirt. It's somewhere. Okay. And my free surface of water is here. Of course. And oil is also there. Okay. I should make first oil above. Oil floats above, water cools below. So here it is still oil. Here it is water. And my plate is here. Okay. And the free surface is from oil is this. Okay. Suppose height of the oil is this much, HO, and height of the water suppose HW. Okay. This is the height of the. Okay. And suppose this is the width of the plate B. All right. Now, first of all, for a high oil, there will be a pressure force by the oil, hydrostatic pressure force of the oil. So hydrostatic pressure force of the oil will be suppose like this. Okay. Till H0, right? Okay. And that will be suppose FP1. Let us say the pressure of this much is FP1 at center of pressure of this diagram. Okay. This is the first diagram. Similarly, it will extend till here as well. So no need to do that for now. Then oil is a constant height, and below that there is a water. So till here, the oil will be from here till here. Now the oil will show a constant pressure because oil was maximum till that depth. So oil will be till here. Okay. But suppose, let us say, this was your first diagram. this is your second diagram from here. Okay. And the third, the hydrostatic pressure of water will also be there, which will be added. So this is your hydrostatic pressure of the water. Okay. So FP1 was this. FP2 or will be this. And FP3 will be somewhere here from the third. So the net FP will be below this line. We can see by the physical sense, right? So the net FP is nothing but suppose like FP, final FP, which you need to calculate. This is your FP. Okay. So this distance is how much? This pressure is how much? Rho of oil, G, H of oil. Okay. This is the maximum. Whereas this much is how much? Rho of water, G, H of water. Okay. H of water. So what will be the volume of the pressure diagram? Volume of pressure diagram is net force FP. Okay, that is your net force FP, and this is sum of FP1 plus FP2 plus FP3, sum of all the FPs. Okay. And volume is nothing but area into width. So width of this is complete B, and area, first area is how much? This is a triangle. First one is the area of a triangle. Second one is area of a rectangle. Third one areas of a triangle. Okay, you get that? So this is your third. 1, 2, and SP3. So that is, or another way, how you can get the FP? A1, H1, A2, H2, A3, S3. So H1, H2, S3 will be different. H1 bar, I can say. Okay. So every FP is having a center of pressure. So let us say this is H1 bar. Let us say this was H2 bar. And let us say this is S3 bar. Okay. Write oil water here. And what will be H bar? That will be here. This is your H. Okay. This is your H1. So one way can be AH bar can be written as A1 H1 bar plus A2 H2 bar plus A3 S3 bar. Okay. So you can get the H value from H bar value from here. Okay. All right. So we got the net FP, we got net H value. All right. Now I'll write the note again. The volume of pressure diagram is the net hydrostatic pressure force on the body and center of gravity of a pressure diagram is center of pressure. And CG of the pressure diagram, I'm saying, of pressure diagram is center of pressure. Okay. Center of gravity for the pressure, suppose this is your pressure diagram. Center of gravity is center of pressure for this. Next point, expression WAX bar is valid for single fluid. So for two or more immiscible fluids which doesn't mix. Immiscible fluids, the hydrostatic pressure force can be obtained by pressure diagram. Okay, by pressure. All right. Now, suppose a free surface is like this. Okay. And my plate is at some depth. Okay. The height is h, as we can say. The center of gravity is here, and center of pressure is here. Okay. So how the pressure diagram will look like for this? How the pressure diagram will look, because it has some hydrostatic depth already. So pressure diagram will look like somewhat like a trapezium. Okay. So this distance is how much? Small a. And this distance is how much? Small b. Okay. Suppose this distance is x1. Okay. The center of pressure is at x bar, and this distance, center of pressure is at h bar. Center of gravity is at x bar. Okay. And this distance, suppose, is at x2. Okay. This distance is at x2. Suppose center of pressure is at, from the base, it has at a distance of y. From the base, let us suppose that center of pressure, it is at a distance of small y bar. Small y bar. Okay. So what will be the pressure force? FP is nothing but WAX bar. But you don't know what is, first of all, y bar, and then what is h bar also. So h bar is nothing but complete x2. From x2 you subtract y bar, you will get your h bar. So h bar is x2 minus y bar. Now what is y bar? You have already seen that y bar from the base is nothing but 2a. So if you are calculating from the base, the twice will be on the a. If you are calculating from the top, then the twice will be on the b. Always 2a plus b upon a plus b into h by 3. So what is A pressure force? Rho g x1. So it will be 2 times rho g x1, 2 times rho g x1. What is B? Rho g x2. It is at a depth x2. Rho g x1 plus rho g x2 by h by 3. So rho cancels out. You are left with y bar is how much? 2x1 plus x2 upon x1 plus x2 into h by. Now put this y bar here. You will get the h bar, the position. Okay. There is one point to note here. If my vertical, the plate is near to the free surface, then h bar is igg sine square theta upon x bar plus x bar. But if my the plate is very deep inside from the free surface, very deep, then h bar will be nearly approximate to x bar. Okay, because the value of x bar has increased very significantly. Point to note here is that suppose my free surface is like this. If my one plate is somewhat like this, and another plate is very depth, at a very lower depth. Okay, so here the x bar is how much? This is your x bar. But here, how much will be the x bar? X dash bar, suppose. So it is very below. Okay. So suppose this is B, this is D, this is B, this is D. Again, same plate, taken much below. So I is how much? IgG. B D cube by 12. Okay. And area is B into D. And H bar will be how much? IgG upon AX bar plus X bar. So if you increase the X bar very high, then this term decreases. So this becomes negligible when you take it very deeply. So therefore, this implies your H bar is nearly equal to X bar for increasing that. So as the depth of the emergent of a vertical plate surface from the free surface, the pressure diagram becomes uniform. So center of pressure shift towards the center of gravity. Okay, always remember. So as depth of emergent or vertical plane surfaces increases, that is X bar increases, the pressure diagram becomes uniform. So center of pressure shift towards the center of gravity. Of okay, always remember this thing. Now let's come to the curved surfaces. Very important, curved surfaces. Hydrostatic pressure, hydrostatic forces on curved surfaces. So suppose, so on a hydrostatic forces on the curved surfaces are in different orientation. So there will be a resultant force, which is a combination of horizontal as well as vertical force, which will act. So if I have free surface like this, okay, and my surface is somewhat like, suppose like this. This is my curved surface. Okay. If I want to make it a three-dimensional, I can make it three-dimensional as well. Okay, this is my surface, and there will be a horizontal force which will be acting always on the surface, and there will be a vertical force. Okay, so there will be a resultant force, vertical force, vertical force, vertical force, horizontal force, horizontal force, horizontal force. So there will be a net resultant force over the surface. Okay, over the surface. Suppose this is at a radius r, suppose like this. So hydrostatic force here, how it is acting? Hydrostatic forces on curved surfaces are in different orientation. So resultant force can be obtained by horizontal and vertical components. That is, your net resultant force is F horizontal square plus F vertical. So how you get the horizontal component? It is again the net hydrostatic force, pressure force exerted on the projected area of the curved surface. On the projected area of the curved surface in a vertical plane. Let us discuss about the horizontal component. It is net hydrostatic pressure force exerted on the projected area on curved surface in a vertical plane. Okay, so what do I mean by this? So this was your free surface. So this is like this. The surface looks like this. Okay, suppose this is a distance x1. Okay, the horizontal component of the force will be like this, which will be acting. Okay, and if I take the projected area of this will be a projected area of the curved surface. Okay, so center of gravity again of this projected area will be at a distance from the free surface. If I say from the free surface, this is your x bar, whereas center of pressure again will be acting here, FP, this was CG, and your this will be H bar. Okay, so X bar is how much? X1 plus R by 2. Okay, so this is somewhat R by 2. So this much distance is R by 2, and this much is X1. Okay, this was from here till X1. X1 plus R by 2. This is your X1. again. So its point of application is again center of pressure of corresponding area. So pressure force, its point of application is center of pressure corresponding projected area. Okay, and again FH will be the same expression, WA x bar, WA x bar. Now coming to the vertical component, so it is the weight of the liquid column above the curved surface up to the free surface, above the curved surface up to the free surface, and its point of application is center of gravity of the corresponding volume. So let me write, it is the weight of liquid column above curved surface up to the free surface above the curved surface and up till the free surface, and its point of application is center of gravity CG of corresponding volume. Okay, so suppose I have like this the free surface, my curved surface was like this. So up to the curved surface, from the curved surface up till the free surface. So this will be your liquid here, and the weight of this much liquid. This will be your vertical force, and this will be FV, and the center of gravity of this volume CG. Okay, center of gravity this volume CG will be your net vertical force. Okay, so how will your final will look like? It will look like something this. So this is your free surface. Your curved surface is like this. Okay. This is your center of gravity. This is your vertical force on this. And this will be your horizontal force, FP, oh, sorry, FH. And your net resultant will be somewhat like this, FR. Okay, and this distance is how much? H bar. Okay, so your net resultant force will be Fh square plus Fv square. And what will be tan of theta if I want to get angle theta, this angle theta? So tan of theta will be Fv by Fh. Okay. All right. Okay. I don't know why my camera was not working so far. Sorry for the interruption, but I hope my audio was there. Great. Okay. Now, suppose there is a scenario that if there is no liquid, the curved surface in such a manner that there is no liquid above the curved surface, then how you will calculate the vertical force there? Horizontal will be same, but how you will calculate the vertical force? case, if there is no liquid above curved surface, like suppose my free surface is like this, and the surface looks something like this. Okay. This is my surface. Suppose this distance is x. Okay. This point is A. This point is B. Okay. And suppose the forces are acting like this. So this is your horizontal force acting. Now how you'll get the vertical force? So if there is no liquid above the curved surface, then the vertical component of the hydrostatic force is obtained by considering the weight of an imaginary liquid column above the curved surface up to the free surface. So what I'll do, I'll draw an imaginary. So this is my imaginary liquid here, up from the bottom till the above the curve, from above the curved surface till the free surface. So this is your imaginary column. Okay, of the same liquid, and the line of action of vertical component is nothing but at the center of gravity of the imaginary column in opposite direction. Okay, so suppose the center of gravity is this of this imaginary column. Okay, then what will be your line of action? This will be your vertical force, and this will be your horizontal force. Okay, and opposite in the opposite direction. So let me write here. If there is no liquid above curved surface, the vertical component of hydrostatic forces is obtained by considering the weight of an imaginary column above the curved surface up to free surface or same liquid. So if there was a water here, you will assume here it is also water. Okay, and the line of action of vertical component is at center of gravity, is at CG of an imaginary column in opposite direction. okay, in opposite direction. So F horizontal will be how much here? F horizontal is again WA x bar, the projected area, and F vertical V, weight of imaginary column. Okay. One column can be like this also. So this is your free surface, this is your curved surface. This can also be a scenario, or like this. This is your curved surface. Again, you have to assume an imaginary column. Okay. Again, that will be the weight. Another case. If instead of one single fluid, you have two different fluids. On both left and right side. Two fluids, suppose, are there. So one fluid surface like water. My surface curved surface suppose is like this. And suppose my other fluid is suppose oil with the free surface here. So this is your oil. This is your water. Again, you will draw the projected area. Suppose this is your projected area of the surface. Okay. There will be a center of gravity. There will be X of water, X bar of water. This is suppose R by 2. Okay. And there will be a horizontal pressure force which will be acting here. This is H bar of water. And the pressure forces F horizontal of water. Okay. Suppose this height is x1. Okay. And this height is x2. Again, you will draw projected here as well for the oil as well. Okay. There will be X of oil and H bar of water also. H bar of oil. So this is X bar of oil. And this is H bar of oil. And the pressure force will be in this direction from the oil. F horizontal of oil, not of water. Okay. All right. Again, this distance is R by 2. The projected area is same. So your F H of water is W of water, area of P into X bar of water. So that is projected area of the water side. The projected area will be same. So projected area is same on the both side. And FH of oil is W of oil projected area into X bar of oil. X bar of. Again, you need to calculate the vertical component. So for the oil, there you have to draw the equal column above. Suppose for the water side, your column is somewhat like this. Okay. So you have to draw an imaginary liquid column. Imaginary column. Okay. And again, center of gravity, suppose is here. So this will be FV, which will be equal to the weight. Okay. So FV of water is weight of water into volume. And suppose the other side oil is there. So this is how much? Radius. Okay. This is equal to radius only. If this is x1, this will be, the height will be x1 plus r. Okay. And on the right hand side, if I have oil, the free surface is of oil. First of all, I'll draw. This is your surface and the oil is here. This was water. Okay. So again, the vertical force will be directly calculated because you don't need to draw any imaginary column. Right hand side, the oil is already there. So this will be this much oil and the vertical force will be Fv. Okay. Fv of the oil. So this was x2. So this distance will be how much? This is r plus x2. Okay, r plus x2. And this is r only. Okay, so Fv, this is acting upward, this is acting downwards. Fv of oil is the weight of oil, rho g into volume. So W of oil I should write, not weight. Sorry. W of water, W of oil to volume. Okay, so net force will be, therefore Fv will be Fv of water minus Fv of oil. Okay, this is a net force. Case 3, suppose you have a circular or cylinder unit. Okay. Another case, suppose this is your free surface and your object is somewhat like this, which is touching the free surface. Okay, this is your cylinder 3-dimensional inside. So you have, suppose suppose I mark the points A, B, C, and D. So horizontal force will be that much only. If I draw the projected area again of this, it will be again the same. So it is x bar okay, and FP will be acting here at CP, that is h bar again, and the whole of this will be of length 2r. Radius of a cylinder is r, so height is 2r. FH will be how much? FP or FH, I should write. FH is W of projective area into x bar. Okay, this is your CG. Okay, now comes the vertical component. So it will be distributed into two ways. So first one is the surface is here. Okay, so there will be this much of liquid which is there. That give me FV1, vertical force 1. Okay, by this much, and this radius is R only. Okay, and this point is A, and this point was D. Whereas the other will be, second will be free surfaces like this. So it will be this much area. Okay. So to find the vertical force above dA, fluid will give you FV1 downwards, and the DC, the section DC, this is your section DC, D and C point, that will be, you will imagine a fluid above DC, and then you will superimpose both of them. Okay. So because of this much liquid till here, there is a vertical force above. So we have assumed that there is a liquid in this liquid. Sorry, there is a liquid here, imaginary liquid, and that is giving me a vertical force like, sorry, so this is my vertical force 2. Okay, so vertical force 1 from here is W into volume. So W is how much? Rho g into R square. This area minus this area. Okay. R square is the square area minus quadrant of a circle, pi r square by 4 into the length of the cylinder. That is acting downward. And here the vertical force 2 is acting upward. That is W into volume. So liquid is same, W into complete R square. This R square, sorry, my bad. This much R square plus quadrant of the volume. That will be W into R square plus pi R square by 4 into, so your net force will be FV2 minus FV1. That will be coming out to be pi W into pi R square L by 2, and this is in upward direction. So this is the net buoyancy force. Okay, net buoyancy force. And similarly, you can take a cylinder with 2 different fluids and the. So I think we can end the session till here, and I'll see you all on the Tuesday, coming Tuesday from 6 to 8 p.m. So all the PDF you will get from the NPTEL team, my Google Drive link, and the link for this recording as well. Those who are new to the channel, all my recordings will be on my YouTube channel. I'll write here. YouTube channel name is NPTEL with Varnit. So in every video description, if you go, the PDF link drive will be there where you will find all your PDFs. So I'll see you on Tuesday. Bye-bye. Thank you so much.